So, hello everyone. Let's get started. And today we're going to start with a new topic, which is distributed database management systems, which is systems that essentially distribute their data over multiple sites. And the relevant chapter in Ramakrishnan and Gerke, that's chapter 21. But some of the things that we are going to discuss in the following lectures in particular will not be covered in this book. So to give you a little outlook of the coming lectures, we're going to discuss first of all about a classical distributed database management systems. This is what we are going to treat in the lecture today. Then we're going to talk about so-called eventually consistent systems, which essentially allow your data to be at least temporarily inconsistent in order to scale up more. That is also part of the so-called NoSQL movement. We're going to discuss that in the coming lectures, probably not yet today. Later, we're going to talk about some systems that support even stronger consistency models compared to traditional database systems, which is also a part of the so-called NewSQL movement. And at the bottom of the slide, you see the icons of a couple of systems that we will be discussing about, such as Apache Cassandra, Amazon DynamoDB, and Google Spanner. So first of all, what is a distributed database management system? That is generally a system that distributes data over multiple sites, and typically the system can run independently at those different sites. There's different variants. We distinguish, for instance, heterogeneous and homogeneous systems, where for homogeneous systems, the different sites are running essentially the same code, while for heterogeneous systems, that doesn't have to be the case. In any case, to the user, this should not feel like a collection of independent systems, but this should be one system that can be queried without having to know, for instance, where the data that you're interested in is located. That is also called distributed data independence. So that is a high-level definition of distributed database management systems, and then there's many different variants. So the motivation for why we want to distribute the data, there's many motivations. Some of the most important ones are here on this slide. One big motivation is availability. If you are, for instance, a large web shop, if you are Amazon, for instance, you absolutely cannot afford that customers cannot reach your website. So instead of running only one single server, you probably want to run multiple servers, and if one of them goes down, then the other ones, they can take the load instead. So availability is a big motivation why you want to run on different servers. Also, perhaps your data is so large that it doesn't even fit on a single machine, then you also want to distribute the data in order to scale to a larger data sets and also to process more queries, for instance, in parallel on different machines. And then finally, there are scenarios where the data on those different sites actually does not belong to one single organization. So those different sites, they might have some sort of autonomy, and perhaps the different sites don't want to completely publish their data, but only make it available under certain conditions and with specific interfaces. So also in this case, you cannot centralize your data because people want to hold on to their own data, but you can create a distributed database management system. So those are some of the motivations to create distributed database management systems. And I have already mentioned that there's a couple of different variants. One way in which we can classify distributed database management systems, that is, for instance, by the architecture. And those three architectures over here, those are the classical architectures for distributed database management systems. We have, for instance, the client-server architecture, where one relatively thin client, which doesn't really store data itself, interacts with a server which does all the data processing, which is relatively simple to implement. But in this model, we essentially assume that all the relevant data is available on one single server, so we don't have to do processing across multiple servers in order to answer one given query. If you want to support that, if you assume that there is queries that relate to data which is stored across different sites, then you might rather want to consider the collaborating server model, where each server essentially stores data locally and can process data locally. But if the need arises, like if there's a query which can only be answered by considering data from multiple servers, then any of those servers can launch a distributed process which essentially coordinates the execution of a query across multiple sites together with other servers. The middleware system is somewhat related to that, with the difference that here we assume there's like some central coordinator which might not store data itself, but just takes care of coordinating the execution of the servers which store data and process it as well. So those are some of the different variants. I'm not going to go too much into detail here, just to give you some first impression for the space of possibilities here. Another important criterion is how we distribute the data across those different sites, actually. And what I can do, for instance, is if I have a very large table which might not even fit on one single site, I could partition it by storing subsets of rows at a specific servers. This is what we also call horizontal fragmentation. As an alternative, what I can do is to rather partition the table not horizontally but vertically, meaning that I store different columns of the table on different servers. That is what we call vertical fragmentation. So in those two scenarios here, we are really distributing the data in the sense that the different servers, they store different parts of the data. What I can also do is a replication, and here that means that different sites store different copies of the data. So here I store the data redundantly, but that can still be useful if I want, for instance, to keep my data secure in case of one site being completely destroyed, or also if I just want to answer more queries on the data in parallel, then it's also useful to have multiple servers storing the same data. Whatever you do, whichever variant of a distributed database system you're considering, in any case, we have to rethink all of those topics that we have discussed for single node database systems in the past lectures. First of all, we already have to think about catalog management, meaning you have to have some way to keep track which data is located where in our system and on which site. We have to think about how to process distributed queries which use data from multiple sites potentially. We have to think about distributed concurrency control, because transactions now could concern data that is stored across multiple sites. And of course, we have to think about distributed recovery, because now maybe not all of your nodes in your distributed system fail, but only some of them. And we have to make sure that if a transaction is processed, it's either processed on all sites or on none of them. So we have to have something like distributed transaction atomicity. So in the following, we're going to revisit all of those topics, and we're going to discuss a little bit about what changes if you go from one single node to a distributed system. First of all, let's discuss catalog management. And we have discussed quickly about the catalog in a single node system, which essentially stores the location and the properties of the data in your database system. If you switch to a distributed scenario, things get more complicated, of course. because now the data is distributed across different sites. So a priori, you don't know where to find the data. There's multiple ways of keeping track of where data is stored in your distributed system. I'm going to quickly go over them in the following. For instance, perhaps the natural choice is to have a centralized catalog. That means there's like one dedicated site which takes care of keeping track of where data is stored. So everyone who wants to know where to find the data they're looking for sends a request to that specific site. As you can imagine, the big problem here is that the whole system becomes very vulnerable to failures of that single site. And there might also be performance problems, because if that site goes down, then people don't know anymore where to find data. And also, if everyone keeps querying that single site in order to find data, that might essentially make that site the bottleneck. So those are disadvantages of the centralized approach. Another possibility would be that each site stores a copy of some global catalog. By global catalog, I mean a catalog which contains the location and properties of all data stored in the entire system. So instead of one site, now every site stores a complete copy of the catalog. And of course, that resolves somewhat the problems from before, because now if one site goes down, it doesn't mean that the other sites don't know where to find data anymore, because each site has its own copy of the catalog. One problem it creates is the following. Now, instead of one copy of that catalog, we suddenly have many copies of that catalog, one on each side. So if something changes, if, for instance, one piece of data moves, or if a new relation is loaded into the system, then instead of updating one catalog, you now have to update one catalog for each site in your system. So you actually have to do a lot of work whenever the data changes. So a third possibility, which is quite popular in practice, is that we have essentially not a global catalog stored at each site, but a local catalog which only covers some part of the data. And here we typically say that whatever site has loaded or created a piece of data will store information about it locally, even in the case that later this relation is, for instance, replicated to other systems. Nevertheless, for each piece of data, there is one site that is responsible for this piece of data and keeps track of where all of the copies of that data are located in the system. So here, each site is responsible for some subset of objects and stores the catalog containing only those objects locally. So if you want to know something about a data, then we have to contact the site which is responsible for that piece of data. Once the site tells us where to find it, then we can continue processing. The advantage here is that in order to move data or when inserting new data, we only have to update the local catalog at one site. One slight disadvantage compared to the global catalog stored at each site is that now, if you don't want to change the catalog but only want to read the catalog, then you typically have to contact some other site in order to get the requested information. But altogether, this is not a bad trade-off between multiple conflicting goals. So those are three classical approaches to catalog management in distributed systems. The next topic we are going to discuss is distributed query processing. Now, let's first of all start with an example. Here we see a query without a join, so it's a relatively simple query, which simply selects the average age from the customers where the customer ID is within a certain value range. So this query could relate to data that is distributed over different sites. And we could imagine that it is either horizontally partitioned, vertically partitioned, or that it is replicated. Can anyone suggest ways in which we can process this query in those different scenarios? For instance, if the data is horizontally partitioned, we have different rows and different nodes. Can anyone suggest a way to process this query in this scenario? Okay, very good. Okay, this is great comments. This actually already relates to an optimization that I wanted to ask about next, but here it comes already. Very good. So here we have a value range of customers that of customer IDs that we're interested in, and assuming that we have partitioned the rows by using the customer ID and partitioning according to customer ID value ranges, such that customers with a similar customer ID are stored together on the same site. If we do this, and if we are lucky in addition, then it will happen that all the interesting customers are located on one specific site. That is the best possible case. In this case, we can process the query locally at that site, and we don't really have to do distributed query processing. Now let's assume that maybe for that value range, the relevant customers are not entirely located on the same site. How would it work in this case? I give you one naive way. I mean, for instance, what we could do is that we just take all the relevant data and send it to one site, and then that one site does all the processing in the standard query processing way. Does anyone have another idea? Yes, okay, very good. So instead of trying to send the raw data to specific sites, which means that we would have to send a lot of data over the network, which can take time, what we probably want to do is that we calculate local averages for each site that contains a relevant data, meaning customers with an ID between 50,000 and 100,000. And in the end, we combine those averages from different sites. In order to get a correct result, we also have to weight the averages from different sites based on how many relevant customers we find on them, but that is most definitely cheaper than the first method. How about vertically partitioned data? Let's assume that we have different columns stored on different sites. All right, yes. Okay, very good. So in this case, we have essentially two columns that are interesting, the ID column and the age column. So we probably want to contact the sites which contain those two columns. And then we have to somewhat combine those columns, those entries in different columns that belong to the same row. So typically when partitioning the columns, then you store tuple ID, which essentially allows you to recompose those split columns into a complete table again. And here we would have to do this for the two columns ID and age, and then we can process the query. So this involves sending around some data, however. So we might, for instance, decide to send the age column from its original storage location to the storage location of the ID column, and then we have all the relevant data on that side, and we can combine it to process the query. And then finally, for replicated data, well, in this case, it's kind of a little bit easier, because here we just have different copies of the same data on different sites. So in order to decide where to process the query, we can, for instance, take into account how loaded, how heavy the load on different sites is at the moment, or for instance, how fast the communication is between whatever site has issued the query and where the data is located. Or in general, we can, if we have sites with different hardware capabilities, then we could try to process the query on a site with more powerful hardware so that it becomes faster. So if we have replicas, then we have some choice about the site at which we want to process the query. So this is high-level overview of the different ways in which we can process queries without joins here. If we have joins, then things become a little bit more complicated. We're going to make an example in the following. Is there any questions about this example so far? All right, no questions for the moment. Good. One remark before we properly start with the joins about execution costs. Now that we are in a different distributed system, we also have to adapt the way in which we estimate processing costs. And we will do this in the following for those join algorithms. So far, we've always measured cost by the number of pages that were read and written, meaning the number of pages that were moved between a hard disk and main memory, because that is the bottleneck of traditional database systems. Now here we have a network connecting different sites, and sending data over that network can actually be quite expensive. So in addition to disk I/O, we also have to consider the cost of sending data over the network. So in the following, we're going to work with two constants. One is the disk constant, and that is essentially the cost per page for writing or reading from or to hard disk. And then we have the constant net, which symbolizes the cost of sending a page over the network. So this is again a very simplistic cost model, but it already gives us some intuition for the pros and cons of different join methods that we are going to discuss in the following. So this is a first query with join. We have a natural join between the customers and the orders. And here we assume that those participating tables are stored on different nodes. Does anyone have an idea about how we can process the join in this case? What would be perhaps the easiest alternative? Yes. So I guess the easiest alternative here would indeed be to send one table to the node storing already the other table, and then the other node can take care of doing the join. Here, for instance. So the first join algorithm that we will see is a version of a join algorithm that we have already seen in a class for single node systems, and that is the block nested loop join. So this is a naive adaptation of the block nested loop join, so we don't expect this to work very well, but just in order to basically in order to show where the difficulties are here. So what we can do is that we essentially proceed like with the traditional block-nested join algorithm, block-nested loop algorithm. We load blocks of data from one table into main memory. And then for each of those blocks, we iterate over the pages from the second table. Now, the second table is not stored locally, but remotely, but nevertheless, we could do it. And once we iterate over the pages of the second table, then we just send each of those pages over the network to the first side. So if doing that, we would have the cost that you see here below. So we first of all would have to pay the cost of reading the pages of the first table from hard disk into main memory on the first side. And then for each block of the first table, we would have to pay the overhead for loading each page from the second table from hard disk into main memory. But before we can do that, we even have to send the page over the network. Therefore, we multiply by the sum of the two constants that we have seen. So we have to send each page over the network and read it from hard disk. So that is the cost here. And it is quite expensive because here we are sending the second table not only once, but actually multiple times over the network, and we have additional costs as well. So that is probably not a very efficient join algorithm. The other possibility, which we have already discussed, somebody proposed that here in the chat, would be that we essentially send all data to one node and then we perform the join there. So if we assume that we send the second table to the side storing the first table, then the cost would be the one that you see here. We have the pages in table 2 times the overhead of sending a page over the network. And then we just add the cost of doing a standard join on that node, number 1, where we pay for the cost of reading table 1 from hard disk. And then we just pay for each block of the first table and each page in the second table. And we multiply that with the disk constant. So this is probably already much cheaper than the previous join, because here we are only sending the second table once over the network. All right. So in the following, we're going to see some a little bit more sophisticated join algorithms. For instance, there is the semi-join. Now, the idea of the semi-join is basically this. We want to avoid sending data from the second side to the first side, which is not useful. So here we are trying to narrow down the part of the second relation that is sent to the first node by first informing the other side about which rows in its relation could be relevant for the join. More precisely, we do the following steps. So, and here we assume that we have an equality join condition, which was the case in the query that we have seen because we had a natural join. And in that case, assuming also one single join column, we would first of all collect the distinct values in the join column of the first table at the first side. Those are values that are interesting in the join column, because if we have rows from the other table with those values in the join column, then they might actually satisfy the join condition. So after collecting the distinct values in the join column, we send it to the other side, storing the second table. And this other side then collects the matching rows which have one of those values it has just received. And it only sends back those interesting rows to the first side. And the first side uses those rows and joins them with the table it stores. this is a little illustration here. So we have those two sites storing data, and the communication between those sites consists of two steps. First, the site 1 sends the distinct values in the join column to site 2, and then site 2 will filter its local rows and send back only the matching rows which have one of those received values in the join column. And then site 1 can produce the complete join result. So here we have a little bit of a trade-off. We are initially sending a bit of data over the network, the distinct values, but that is hopefully not too large. And then we get a reduced number of rows from site 2 over the network. And if the matching rows are significantly less than the entire rows, then this semi-join was a good idea. Now, in some cases, sending all the distinct values in the join column can actually be expensive. So the next join operator that we will see tries to minimize the amount of data that is sent initially from site 1 to site 2. This join uses a so-called Bloom filter. And a Bloom filter is generally a data structure that tries to represent a set in a very compact manner, but it has a drawback. It doesn't tell you precisely which elements are in the set, but it sometimes produces false positives. So you will see elements that are not actually in the set. The way it works is using a hash function. So the Bloom filter is essentially a vector that stores 1 bit for each bucket of a hash function. And this bucket is set to 1 if there is at least one element in the set whose hash value falls into that bucket. If there's no element in the set whose hash value falls into the bucket, then the bit is set to 0. So if I'm analyzing this Bloom vector and I see a bit set to 0, I know for a fact that no corresponding element can be in the set. But if the bit is set to 1, I know that some elements whose hash value fall into that bucket are in the set, but I don't know which ones precisely. So some information is lost in the process. Here I'm illustrating that. So on the bottom of the slide, you see the original data. Then we apply the hash function, which is represented by those green arrows, which point to the associated hash bucket in the Bloom filter. And here you see in the Bloom filter, we have those bits set to 1, where we have at least one associated item in the original data set. So the Bloom filter is smaller than the original data, as you see here. But on the other side, it is also less precise and loses some information. All right. So the way we can use such Bloom filters in the join is, as you see here, we again, as for the semi-join, we collect the distinct values in the join column of the first table. Then, and that's new, we approximate those values by a Bloom filter. We send this Bloom filter, which is fairly small, to the site which stores the second table. And then we collect rows there that potentially match values in the join column. Now here we say potentially match because we have only a Bloom filter, so we cannot be sure that specific rows match any rows in the first table. Now we send back those potentially matching rows, and then on the first side, we perform the join. So here, again, there's a trade-off. In step 5, you might actually send some rows that are unnecessary, which is bad. But on the other side, in step 3, we send a Bloom filter, which is much smaller than the set of distinct values, which is good. So there's a trade-off. This is an illustration. It is, again, a two-step communication like for the semi-join, but the data that is communicated differs. In the first step, site 1 communicates the Bloom filter to site 2. instead of the actual values, which is smaller but also less precise. And then in the second step, side 2 communicates some superset of the relevant rows to side 1. So that might be a little bit larger than before, but hopefully not too much. Okay, and this is a great question, okay, about how this relates to catalog management, and whether if we would use a global catalog stored at each site, probably whether we could avoid sending the unique values from one site to the other one. So that is a great question. I mean, in a database, a catalog, sometimes we have some high-level information about the content of a specific tables. That is absolutely correct. But typically, the catalog doesn't store information at the granularity of a single values. So even if you have access to the catalog, it probably won't give you very precise information about the specific values in the join column. But nevertheless, this is actually a great point. One could say, maybe I want to avoid sending data from site 1 to site 2 altogether. But if site 2 can somehow use the catalog in order to exclude that certain rows are relevant, then it should do that. And in that way, you might also be able to reduce the number of rows that you send back from site 2 to site 1. So it's a great point. In some cases, you could get some useful information from the catalog, which allows you to discard some rows before sending them. But the information from the catalog will be very coarse-grained. So even if you have access to the catalog, there is still motivation for sending either the Bloom filter or some set of values. Okay, good. Is there any other questions about the different join operators? So this is here just one little summary, but I have already said that the trade-off between semi and Bloom join is that the semi-join sends a little bit more values from site 1 to site 2, but receives less values from site 2 to site 1. The Bloom join sends a little bit less data from site 1 to site 2, but might receive a little bit more data sent from site 2 to site 1. And which one works best depends on the scenario. Is there any questions about joins in a distributed setting? All right, I guess currently not. One word on a distributed query optimization. So we have discussed a lot about query optimization on single node systems, and the principle still pretty much stays the same for distributed systems. There's a couple of changes that I'm quickly gonna discuss in the following. So first of all, of course, you need a new cost model. We have already seen that a little bit. We have introduced the new cost components for measuring the cost of sending data over the network. Also, we have new choices about operators in a distributed setting. Here, for instance, we have seen a couple of join algorithms that are specialized for a distributed scenario. And then finally, we have not seen that here, but I have quickly mentioned that one of the motivations for distributed systems is that different sites might not want to completely share their data and retain some kind of autonomy. That is also something that we would have to respect in query optimization, because if those different sites are managed by different organizations, then perhaps the query optimizer cannot fully control them in query processing, but only can make something like suggestions and needs to remain flexible in case that the site essentially refuses to process certain operations. I'm gonna quickly have a look into the chat if there's questions. Okay, very good question. Okay, very nice. Okay, so here the question is, if you have a key foreign key constraint between the join columns in the two tables, then we can actually be sure if our data is consistent, then we should assume that every foreign key actually corresponds to a key in the other table. And if we have this case, then maybe there is no point in actually sending any Bloom filter or any distinct values in order to try to narrow down the set of rows that are received. So that is a great point. And as long as we don't have any other predicates in the query, yes, if we have one single joint predicate and no unary predicates, and we have a key for a key constraint, then you know that for every foreign key, you must have the corresponding key. And I totally agree in that case. You can avoid actually sending the Bloom filter or distinct values. That changes in case that you have, for instance, a unary predicates. So in this case, it might turn out that some of the rows on the foreign key side don't match anything on the key side, because the corresponding row has been filtered out by a unary predicate. So depending on which of the two sides initiates the distributed join, so which one is side 1 and which one is side 2, it might still make sense to send values in between, because the side of the storing the key table with the unary predicates might want to tell the other side which values in the join column belong to rows that have passed the unary predicates, and then we can also reduce the amount of data that is sent between the different sides. But yes, if you don't have unary predicates, then I fully agree with that. Very good point. Okay, great. Is there any other questions about this for the moment? All right. Then let's continue to distributed concurrency control. And I mean, as for all of those topics, I'm mostly focusing on what changes compared to concurrency control schemes that we have seen for single node systems. So the general challenge here is, of course, that now transactions might actually access objects that are stored across different nodes in your system. And that means it is insufficient to perform local concurrency control, but we somehow need to coordinate across multiple sites. One popular concurrency control method that is also used in the distributed setting is, again, two-phase locking, which we have discussed in the lecture before. If we port that to the distributed setting, then two important questions we have to answer is, first of all, where we want to store the logs, because there has to be some kind of registry which says that a specific transaction is currently holding the log on one specific object. And as long as all objects are stored on one side, there is no question. But if those objects are stored across multiple sites, we have to think about who is actually storing the logs. Also, we have to think about how we want to handle deadlocks, because now a deadlock could actually involve multiple different sites, and you would not recognize it as long as you only consider things that are running on one specific site. Now, with regards to the first question, there's again a multiple possibility. We could decide to have one centralized log manager site that manages all the log requests, but similar to the drawbacks when using the centralized approach for catalog management, also for logging, we introduce high vulnerability, because if that site goes down, then everything stops. And also performance might actually become challenging. Another popular approach to distributed log management is the primary copy approach. And that means that for each object, even if it is copied across multiple sites, there's always something called the primary copy stored on one side, and the site storing the primary copy is responsible for managing logs on that object, including all of its copies. Now, here we don't have this single site vulnerability anymore, but on the other side now, in order to issue log requests, you probably have to communicate with some remote site still. The last possibility would be to fully distribute the logs. So essentially, each site manages the logs for all the objects that are stored there. And if there's multiple copies of an object at different sites, then the logs for those different copies are managed by different sites. And that means that when requesting logs for objects that are stored locally, we don't have to send requests to necessary to other sites. But if we want to write, for instance, then we still have to do that. So as for the other mechanisms, it's difficult to say that one of them works best, but all of them offer different performance trade-offs, and then it depends on the particularities of the scenario, which of them you want to use. When it comes to deadlock detection, we again have the possibility to have one centralized component that essentially obtains the weights for graphs from all the single sites. And as a little reminder, a deadlock, that is essentially a chain of transaction waiting for each other in a cycle such that nobody can make progress. And the way to detect deadlocks is to look for cycles in this weights for graph, which essentially tells you which transaction is waiting for logs from which other transaction. And we could, in principle, have one dedicated site that gets sent all of the weights for graphs from all the different sites, but then that central site would likely become the bottleneck, and it would be vulnerability if it fails. So another thing we could do is to make a hierarchy of sites, and then to essentially forward the weights for graphs to the next higher level of the hierarchy. So in this hierarchy, parent site essentially gets information from all the child sites and tries to detect all deadlocks that it can, given the information that it has. If it doesn't detect any deadlocks, then it will pass on its information to its own parent. So the parent has even more overview and might detect more deadlocks that involve different sites, until finally, at the root of this hierarchy, we have all the information available and can therefore detect all the deadlocks. So that reduces the load on single sites. On the other side, it may take a little bit until the required information has propagated up this hierarchy and until the corresponding deadlocks can be detected. One simple way that is often used to detect deadlocks, even if it has some drawbacks, is to simply set a timeout and assume that a deadlock has occurred if a transaction cannot make progress until the timeout. So this is very easy to implement, of course. The drawback on the other side is that we might sometimes have unnecessary aborts because a transaction was just slow, but not really in a deadlock. So this is a quick overview of the different approaches to distributed deadlock management. All right. Now, the final topic is a distributed recovery, but we are now reaching the end of the time slot. This is why I'm going to save that for next time. We would have time for one more question if anyone has a question about the things that we discussed so far. If there's no immediate questions, then I wish you a nice day, and then I see you again on Wednesday.